Hi, today we're going to talk about what vapor pressure is and how the Clausius-Clapeyron equation links temperature, vapor pressure, and the heat of vaporization. Normally, when you think about a liquid turning into a gas, you think about something like having a pot of water on the stove. Get any liquid up to the right temperature and it will turn into a gas, right? Actually, anytime you have a liquid open to the atmosphere, you'll have liquid molecules going into gas phase. It's why I can fill this cup with water and leave it outside for a few days and come back to find it empty. And it's why when you take the lid off a bottle of nail polish remover, you smell it. The scent receptacles in your nose only detect gases. The reason you smell that acetone is that part of it has turned into gas. Vapor pressure is basically the partial pressure of a particular gaseous substance that forms above the liquid form of that substance. The vapor pressure of a substance is dependent on the intermolecular forces holding that substance together. For example, take hexane, C6H14. This is a nonpolar molecule that only has London dispersion forces, which come and go, so there are relatively weak forces holding it together. By contrast, water molecules are held together by hydrogen bonding, which is much stronger than dispersion forces, so water will have a lower vapor pressure than hexane. The higher the intermolecular forces, the lower the vapor pressure. Given that knowledge, let's look at a series of 3 molecules and try to arrange them in order of vapor pressure. We'll do this by thinking about the intermolecular forces, and in order to do that, we have to evaluate whether or not the molecules are polar. So gasoline, which is mostly octane, C8H18, has only carbon-carbon and carbon-hydrogen bonds, and none of those will have a very big electronegativity difference. So gasoline will have no dipoles. Anytime you have a non-polar substance, you will have London dispersion forces holding your substance together. How about water? Well, water has hydrogen-oxygen bonds, and given the huge electronegativity difference between hydrogen and oxygen, that means it contains strong dipoles. Water molecules will be held together with hydrogen bonds. Now let's look at acetone. As you can see, acetone is going to have carbon-carbon and carbon-hydrogen bonds, which are not going to be polar, but it does have that one carbon-oxygen double bond that will be polar, so we will find acetone to be polar. But they're not strong dipoles like what they have in water. What we have are dipole-dipole forces. So what does that tell us about vapor pressure? Well, gasoline only has London dispersion forces, the weakest intermolecular forces, so that will also have the highest vapor pressure. Water has the strongest intermolecular forces, so it will have the lowest vapor pressure. And that means acetone will be somewhere in the middle. We also observe that the vapor pressure of a substance is dependent on the temperature. Why is that? Well, remember that temperature is the measure of the average kinetic energy of a system. That doesn't mean that all molecules in a system have the same kinetic energy. To understand this, let's look at a graph. On the x-axis, we'll show the kinetic energy of a molecule, and on the y-axis, we'll graph the percent of molecules in a system that have that kinetic energy. The graph for a particular system might look like this. As you can see, there are a wide range of kinetic energies, but some of them are more common than others. And you can easily see where the average kinetic energy for the system is. Now, in order for a molecule to escape the liquid phase and turn into a gas, it will need to be moving with enough kinetic energy to break the intermolecular forces holding it back. We'll indicate that energy here. Any molecule with an energy equal or higher to this energy will turn into gas. Right now, you can see that's a fairly small fraction of the molecules. But what if we turn up the temperature in a system? We might get a curve like this. If you look at the average kinetic energy for this green curve, you see that it's higher than that for the brown curve. That's how we know it's a higher temperature. And now look at the percentage of molecules that have enough energy to escape. It's much higher than before. You can imagine that there will be a temperature where even the average kinetic energy gives a molecule enough energy to escape, and that's where you're going to see large-scale boiling like you'd see in a pot of water on the stove. So here's a question. Do solids have vapor pressure? What does that question even mean? Basically, one concrete example is, if you observe a desk or table, will you see any cellulose molecules come flying out into the gaseous state? Most people would say no, because no one has ever seen a desk evaporate. I mean, my desk at home is the desk my dad used when he was back in grad school, even before I was born, and it still looks pretty solid to me. But let's think about a few questions. Do the molecules in a solid move? Well, they do, just not as fast as they do in a liquid or gas. We know they move because all molecules above the temperature of 0 Kelvin are moving. What controls how fast the molecules move? Well, intermolecular forces do. The stronger the forces, the less the molecules can move around. And solids have pretty strong intermolecular forces compared to liquids. But there's also the temperature factor. The higher the temperature, the faster on average the molecules will move. So how does that relate to solids? Well, let's look back at our graph. Remember that we saw that the percent of molecules that escaped was smaller at lower temperatures. For a solid, the average kinetic energy is much, much lower than the escape energy. There will always be a fraction of the molecules that can get away, though. Don't believe me? Think about all the fragrant solids in your life. Smell some cedar. Unwrap a bar of chocolate. And remember that if you smell something, it's because it has a vapor pressure. So now let's talk about that escape energy. First of all, that's not a real term. It's something I made up to explain this concept to you. In general, we use specific terms to describe the energy for a given phase transition. So for solid to liquid, we'd have one term, the heat of fusion. And for the liquid to gas transition, we call that the heat of vaporization. We write it this way. And because it's delta H, you know this is an enthalpy. So how do you know what the heat of vaporization is for a liquid? When you were doing enthalpies in lab, you used calorimetry, but that technique only works well for heats of reaction. It doesn't work well at all for vaporization. So we need to think of a way that we could measure stuff in lab to find the heat of vaporization. And luckily, we have an equation that will help us do that. It's called the Clausius-Clapeyron Equation, and it looks like this. As you can see, this equation contains the heat of vaporization. We also have the vapor pressure, or rather the natural log of the vapor pressure. So you can already see there must be a relationship between vapor pressure and the heat of vaporization. What else do we have here? The gas constant. Again, there are many forms of the gas constant, but in this case we're dealing with energy, so we're always going to use the form that contains the energy units, joules per mole Kelvin. Finally, we're going to add the temperature because as we saw earlier, the number of molecules that escaped the vapor pressure was not only linked to heat of vaporization or escape energy, but also to the average kinetic energy of the molecules, also known as temperature. We also have a constant that's not really all that important to us. Now, what I want to do is think about this equation in algebraic terms. I've rearranged the equation a little here and now compare it to the generic equation for a line. And you can see that we can set this up to be a linear equation where y is the natural log of p, m is negative heat of vaporization over r, x is 1 over t, and b is this constant. So if you have experimental data showing vapor pressures at different temperatures, you can graph natural log of p on the y-axis, 1 over t on the x-axis, and the slope of your line will be the negative heat of vaporization divided by r. So here's an example of some experimental data graphed like that. We can do a linear fit to get the equation for the line. And now remember that the slope is the negative heat of vaporization divided by r. So the heat of vaporization then would be equal to negative r times the slope. This means that the heat of vaporization for this particular system is 40,700 joules, 40.7 kilojoules. This equation, the way it's written, is really useful for lab. But if we're working with calculations on paper, it's actually not so much. Usually for that, we use what we call the two-point form of the Clausius-Clapeyron equation, which looks like this. I'm not going to derive this for you unless you really want, in which case leave me a comment down below and I'll make a different video that does that. As you can see, this has the same basic form, except now we have a ratio of vapor pressures on the left side of the equation, and the difference between the inverse temperatures on the right side of the equation. Basically, we're relating pressures and temperatures from two different situations. Using the two-point form of the Clausius-Clapeyron equation looks like it might be a plug-and-chug situation, but equations of this sort, and we have a few in chemistry, tend to be things that people mess up on a lot. So I've developed a few tips to help you get the correct answer, which may not make a lot of sense when I explain them up front, but will become more clear as we work through problems. First of all, the two-point equation is based on two different conditions, and you need to figure out which pressure belongs with which temperature. It does not matter which of the sets you choose for condition 1 and which you choose for condition 2, you'll get the same answer no matter what you do, but just make sure the pressures and the temperatures belong together. Secondly, check your units, make sure they match. You have 2 pressures. They need to have the same units. You'll have 2 energy units, the heat of vaporization and the gas constant. Make sure the units on those match. And then the temperatures always have to be in Kelvin. Thirdly, make sure you use the right form of the gas constant. It's got to be 8.314 joules per mole Kelvin. Fourth, there are a lot of calculations here, and it's not always easy to put the numbers in your calculator the right way. I tend to write answers to subparts down on my paper in case I mess up and need to start over again. That way I don't have to go all the way back to the beginning. Finally, hang on to those decimal points. Don't round until the very end. This is something you should always do, but because especially now in this one we have logarithms and exponents involved, even a difference of 1/100th can make a noticeable difference in the final answer. So those are the tips. Now let's apply them. Here's our first problem. We're solving for the heat of vaporization for toluene based on 2 sets of conditions. So let's identify which pressures and temperatures belong together. So the problem says here that the vapor pressure at 20 degrees Celsius is 21 torr. That is one set of temperature and pressure, and I'm going to call that condition 1, which means that P1 is 21 torr and T1 is 20 degrees Celsius. Now, of course, we have to convert that to Kelvin. So here's T1 in Kelvin. Now we need another pressure and temperature set for condition 2, and here's what we've got according to the problem. There is an obvious temperature here. T2 is 111 Celsius, which we can translate into 384.15 Kelvin. But what about our pressure? Well, this says normal boiling point, which is a phrase you see a lot in Clausius-Clapeyron problems. What that means is the temperature at which that substance boils at sea level, 1 atmosphere of pressure. Pressure 2 then is 1 atmosphere. But we can't use it that way in the problem because our other pressure is in torr. We need our pressure units to match. So we either need to convert P1 to atmospheres or P2 to torr. And I'm going to do the latter one because I know that 1 atmosphere is 760 torr. I don't need to break out my calculator. Now we have our numbers. Let's plug them into the equation. And now that the numbers are in there, let's break out our calculator. Let's make sure we plug in R, 8.314 joules per mole Kelvin. Now what I'm going to do next is calculate the individual parts of the equation, the ratio of the 2 pressures and the difference of the inverse pressures. Now it's true, I can do this all on my calculator using parentheses in the right places, but even if I do that, I always write down the little sub-calculations along the way because it makes checking my answer a lot easier. I also try not to round too much. Now I solve for the heat of vaporization and I get 36,924 joules, which is also 37 kilojoules. Now you don't have to convert to kilojoules, but if you do, it's a good time to check your significant figures. Now, as you can see, that's a messy bit of math. So to familiarize ourselves with this equation, let's do another problem. Now this problem is set up differently. We are not solving for the heat of vaporization. We're actually given that. Instead, we're solving for a vapor pressure. Let's start by picking out our 2 conditions, condition 1 and condition 2. Here we have a vapor pressure of 70.4 torr that corresponds with a temperature of 0 C. I'm going to call that condition 1. Again, it does not really matter which is which. You get the same answer either way. If you don't believe me, try it both ways. Now my default is to label the first one I meet in the problem as number 1, but you could do the opposite, it doesn't matter. Anyway, P1 is 70.4 torr, T1 is 0 Celsius, which of course is 273.15 Kelvin. Now our condition 2 has to be this here. We don't know what the vapor pressure is, that's what we're trying to figure out. But T2 is 25 degrees Celsius, which is 298.15 Kelvin. Now let's take this information and plug it into the equation. Remember, we need to check units. Pay special attention to this term right here, which is where we often find a unit mismatch. And indeed, we have one here. Our heat of vaporization is in kilojoules, and our value of R is in joules. I'm going to convert the kilojoules into joules. That gives us this. And now I'm going to break out the calculator. I run everything on the right side first, and what I get is this. The natural log of the ratio of our pressures is equal to negative 1.15568. Now, for some of you, it may be obvious how to keep going, but if it's been a while since you did logs, know that the way to get rid of a log function is to do the inverse function, the exponential function. The inverse of the natural log is going to be e to the whatever power. So let's do e to the power of each side, and then we simplify. E to the natural log of anything is just anything. So our left side is just that pressure ratio. And the right side is whatever e to the negative 1.15568 is. You do that on your calculator, and that ends up being 0.31484. So now let's solve for P2, and that pressure ends up being 224 torr. The Clausius-Clapeyron equation contains some messy math, but just remember, practice makes perfect, so try a few more problems. Once you master its use, it's very useful for determining vapor pressures and heats of vaporization. I hope this was helpful, and I'll see you again soon.